All right.
All right.
So are you a PhD student, Khan?
Yes, I'm a PhD student with Suhas Digawai.
So you're okay. So your professor is Suhas. All right. Cool.
Yeah.
So yeah. So this time we're gonna do a little bit different than before. So I mean, we usually like give list of papers outside UCLA, but I think sometimes it would be also nice to share papers inside UCLA. So how do you pronounce your name? Is it Khan or?
It's Khan. Yeah,
Okay.
Khan.
All right, Khan. Go ahead.
So yeah, this work with it was joint work with Navjot, Dipesh, and Professor Digawai, and it was published last month at NeurIPS 21. So I will first talk about our setting, and then I will briefly also mention about the general federated learning setting. So in our setting, assume that there is a server and there are many clients, and each of the clients are trying to come up with some individual models, but their data is not huge, so they also want to collaborate with other clients through this server. So in our setting, there are some differences. For example, in our setting, the clients can have different resources, so they want to use different architectures or different quantization precision, for example, and they also have access to possibly data sets which are heterogeneously distributed across the clients. So for example, one client might have some pictures from a snowy area and they're trying to make some classification test. Another can have some forest. So briefly, I want to briefly mention the federated learning framework. Basically, a server is trying to find a global model that minimizes the average loss across clients. So this is like the regular setting. And now when the heterogeneity comes into play, a single global model might result in poor performance because you basically try to use a single model to fit into different data sets. So this might be a problem.
Can you define heterogeneity?
Yeah. So let's say at each client we have some underlying distribution DI, and your data set is sampled according to DI. So in the homogeneous setting, for example, in the regular distributed training, DIs are assumed to be the same. But in the heterogeneous setting, DIs could be different. So that's the difference.
Okay, got it.
And in the conventional federated setting, there is like this implicit assumption that the clients can have different resources, but it is not explicitly stated in a formulation. So first, due to this heterogeneous and because a global model can perform worse, people come up with this personalized federated learning schemes, and they propose schemes where each one of the clients possesses its own personalized model. However, these previous formulations do not capture the resource heterogeneity. So in this work, we also capture that. And the resource heterogeneity comes into play with, might come into play with different architecture. So one client can have a ResNet 8, one client can have a ResNet 20, and also can have different precisions. One client can use 1 bit and the other can use 3 bits, for example. Yeah. So I will just briefly mention the quantization part of our work first, and then I will mention about the personalized federated learning setup. But I will just skip through the quantization because it's not very related to the course itself.
Khan, quick question. At the end of the day, you will train multiple models. Each one is tailored for one of the devices, or you come up with like a centralized model that everybody just query that model. Which one's gonna happen?
The first one is going to happen. What matters is the personalized model, and the global model actually does not perform very well. It just acts as a collaborator or like, you know, some tool for communication. So it's, if you look into in terms of privacy, it's actually a good thing because the global model is shared across devices, but it isn't critical. The critical thing is the personalized model.
I see. And then, so the idea here is that there are a bunch of different data sets, all for the same tasks.
Yeah.
And then not every node has all the data. So you kind of like the server acts as an intermediary to collect this information and share it with everybody else.
Yeah, exactly.
Right? Okay. All right, go ahead.
All right, so model quantization. Here, what we mean by model quantization is basically you're trying to quantize a neural network itself. So, for example, I don't know if you can. Yeah. So here you have full precision weights. Let's say this is like a fully connected layer, and it has some weights. And here you have some quantization centers that are the values that you're mapping to. And here the mapped version or quantized version of the neural network. So this is like a code book in that sense. So in our work, we will learn both the mappings from these weights to which of the codebook entries you are mapping to. And also we will also update the codebook entries as well. So it's like a dynamic approach. So you're it will be like an alternating optimization problem. So for that, we propose a relaxed optimization problem where you optimize over X and C. X is the regular neural network weights and C is the codebook entries. And here Fx is the neural network loss. Fq tilde Cx is like the neural network loss of the quantized neural network. And R is a penalty function that forces you to be close to your quantization centers. I mean, yeah, if you're interested in more of this, you can ask me or you can read the paper. So this is like, yeah, it would take so much time to talk about this actually. But yeah, but Q tilde is a soft quantization function, so you can take the derivative. But in the end of the training, you convert it to a hard quantization function. Yeah, so this is like the alternating proximal gradient.
One more quick question is that the number of code books is already known, right? So
yes,
this is like a given in your training, say 2, 4 or something, right?
Yeah, exactly.
The only thing is that you need to find what those code books should be in order to minimize the error.
Yes,
correct?
yes. So each client can specify its own desired number of codebook entries. Yeah. Yeah. So this is like the alternating proximal gradient steps. Proximal gradient is just you do the regular gradient step and then you kind of do a soft thresholding or soft projection towards the center. So yeah. So we have, in this paper, we have some theoretical results as well as some experimental results. And the first theoretical result is about this centralized case. So right until now, we didn't have any communication between some server or some sort of, we only had this model quantization scheme. And according to this scheme, we see that this is the first order guarantee for convergence. And we basically see that choosing a smoother Q tilde will speed up the convergence. But if you're not aggressive about this Q tilde or you are choosing it too softly, then in the end, when you do a hard quantization function, there will be an accuracy loss. All right, so now we will have this understanding of this model quantization scheme, and now we will look at the more interesting part, the collaboration part of the paper. All right, so previous works, in general, they try to how can I say this? They try to prevent this local or individual models to drift away from the global model so that each of the local models are related to each other. and they have this information sharing through the global model. But what the previous models did is to use, for example, some type of penalties like L2 distance between the models, like the neural network itself. However, this could work when all the models have the same architecture, but it doesn't work when the all models have different architectures. So that's why instead of such an L2 loss, we use knowledge distillation, or basically KL divergence between the classification scores of different models. So yeah, basically this way we are enabling the collaboration of different architectures. And yeah, it also performs well in the experiments. So now we are trying
SI in that formula was the global model.
SI?
It's the right one.
This
is just the ground truth.
No. This is the output scores. So let's say we give a data point to a local model. It generates an output score, right? Like this softmax score. And let's give the same data set to the global model, and it also generates the output score. So we use the deviation between those output scores to enable the collaboration. And since we are only looking at the output scores, it doesn't, we can basically combine different models with different architectures, because the important thing is.
Yeah, I understand that, but I was just asking about the notation. So SIWs are your local models and SIX is your global model, or is it the other way around?
This is, yeah, the other way around. This is the local and this is the global.
Okay,
and,
got it.
Yeah, SI is the function that generates the softmax outputs, basically.
Correct.
Input, yeah.
I see. Okay, got it.
So where is the data set come from? Where does the data set come from? Like
yeah, so that's a very good question. Data set resides only in the client, so you don't share any data with any other client, and you don't share it with the server. But servers model can see the data, so it might be, that might be in future work where you're trying to introduce, for example, differential privacy or other tools, so that even you can basically do that in the future as well. But the data resides in the local client only. Yeah, so this is called, like, data-free collaboration. It basically means that you don't have any public data set or something like that to do this knowledge distillation. You use your own data. All right. So yeah, so now we will introduce the augmented optimization problem to allow the collaboration. And if you recall, for the centralized case, we had this optimization problem. This is the relaxed optimization problem we were trying to optimize for model compression. And now we will have this additional term where you are trying to minimize also. So basically, you are trying to minimize the deviation between the output scores of a local model and the global model. And this allows you to collaborate. Yeah, and the overall problem is this one. As you see, the optimization variables are W, which is a global model, XI, which is the personalized model, and it can have different dimensions, and CI, the codebook entries. So with this optimization problem, you learn 3 different things, but the W is just for collaboration. It's not very critical. The important thing is XI and CI, because in the end, you will hard quantize XI using CIs. So these two are the most important things to learn. So let me briefly talk about, I don't know if I have time. I'm running out of time, I think, but All right. So basically, this also allows some local iterations, which is something expected in federated learning schemes. So let's say we have an initial global model, server broadcasts this initial global model to the clients, and using that, clients do this alternating optimization steps. And then here we update the global model also, and then we send the global model to the server, but we don't send our personalized models. And in the server side, it takes the average of all the global models that it received from different clients and generate a new global model. And then the server broadcasts this model to the edge devices. So for the convergence result, there is actually a nice result that we discovered here. Basically, we saw that clients having local data that is not a representative of the general distribution need to choose models or functions with a small smoothness parameter. Or for example, clients whose data is too far apart from the other data needs to choose a less aggressive compensation for a nice convergence result. And clients with data that is representative of the overall data distribution can tolerate having more quantization, for example. Yeah. So in the experiments, we compared to some personalized federated learning methods, these three. Although all of them are in full precision and these two are quantized to 1 bit and 2 bits respectively, our algorithm can almost, when our algorithm is used with full precision, it outperforms the other methods. But even when we do an aggressive quantization, such as 1 bit or 2 bits, it still either outperforms these methods or it's very close to them. And we use 3 different data sets for this experiments. We also checked a case where how the communication of different neural networks, different models work. And compared to local training, it performs really well. We couldn't compare to other methods because their formulation does not allow this setting. And that's it. Yeah. Thank you for listening to me.
All right, thank you so much. Are there any questions? Have you presented this yet?
Yeah, I presented it. Yeah.
Okay. Yeah, nice work.
Yeah, thank you.
All right, so moving on to the next group. Are you there?
Hey,
Shingyue
we are
and
here.
Yes, hello.
hey, how you doing?
Yes,
So
well, thank you, Professor.
can you start sharing your screen?
Okay, I will share my screen.
Cool.
Can you guys see it? Oh,
Yes.
I see there's a. Oh, no. Okay. Then we started.
Please.
Hello everyone. The topic we are going to present is low latency privacy preserving inference. I'm Mingxian and my teammate is Shen Hui. And this is our outline. First, we will go through the problem description and then give some background knowledge. Following, we will talk about the main solutions and contributions of this paper and how they evaluate their methodology and their main results. Finally, we will have a little discussion on our insights and end with reference. Problem description. This work is basically the following up of previous CryptoNet work. There are still limitations when applying homomorphic encryption to the inference of neural networks. First, the latency is very high. CryptoNet takes 205 seconds for a single prediction with only approximately 59,000 predictions per hour. Second, the memory usage is also very large because CryptoNets encode each node in the network as a separate message. It requires hundreds of gigabytes of memory. Third, the depth of network is limited because more addition and multiplication operations result in increased level of noise. This causes the growth in message size to accommodate the noise. Background knowledge. Here we are going to introduce polynomial ring, since it is not mentioned in previous lecture and presentation. Polynomial ring is the domain where homomorphic encryption operates on. Both encrypted data and unencrypted data are represented by polynomials. The coefficients are all integers, and they are always the remainder relative to some positive integer p. This is mode p. For example, let p be 24, then all coefficients are in the range from 0 to 23. This form a ring as shown here. 21 plus 3 plus 6 will become 3, and so on and so forth. Besides, the coefficient can also range from -11 to 12. It's okay no matter the remainder is -1 or 23 when dividing by 24. And moreover, the idea of remainders also applies to the polynomial themselves. Here we define a polynomial modulus x to the power of d, where d is 2 to the power of some n. The same concept repeats here. The polynomials are also always the remainder after they are divided by the polynomial modulus. For example, let n be 4, so d will be 16. Then the polynomial modulus is x to the power of 16 plus 1. Thus, we only consider polynomials with highest degree ranging from x to the power of 0 to x to the power of 15. Any higher degree will be reduced by polynomial modulus. For example, x to the power of 16 will be replaced by -1. And therefore, all the polynomials we considered are of the following form as shown here. And we can view each term with its coefficient as a ring. And 16 rings together form a polynomial ring. Every addition and multiplication operation is performed on these rings, and the resulting polynomial will still conform to this form. We can also see that there are green dots on each ring. Each dot represents the value of coefficients. So this graph exactly represents a polynomial. In this paper, the homomorphic encryption scheme they used is BFV scheme. As we learned before, the addition and multiplication on encrypted data and then decrypt it will result in the same result as performing addition and multiplication on plain text. Here, x1 and x2 belong to polynomial ring R, and the notation of R here is exactly the same idea as we discussed in previous slide. Another note is that if parameter p and d satisfy some condition, then every element in R can be viewed as a vector where addition and multiplication operate component-wise. So we first transform normal data into polynomial, and now we can further translate polynomial into vector. Therefore, in the following presentation, we will all discuss over vector, but essentially it is mapped to polynomial. In this paper, there are 3 available operations on the encrypted data: element-wise addition and element-wise multiplication between vectors matrix, and we are quite familiar with. And they also used in previous crypto network, but the rotation operation is newly proposed in this paper. There are row rotation and column rotation. Below are some examples. The middle one is the original matrix rotated by 1 row, and the right one is rotated by 1 column to the right. Since the goal of this work is to improve CryptoNets, so we will briefly review CryptoNets. It's a convolutional network with 4 hidden layers. It replaced nonlinear operations such as ReLU, sigmoid by square activations. And it only uses additions and multiplication operations between vectors and matrices. No rotation operation. It can reach 99% accuracy on MNIST with 205 seconds latency for single prediction. The throughput is approximately 59,000 predictions per hour. The high throughput of CryptoNets comes from the vector structure of encrypted messages. Each message can encode a vector of dimension n, and n input data can encode simultaneously as shown below. Assume there are 4 input vectors with dimension 4, then we can encode all the value in the first position into message 1 and values in second position into message 2. and so on and so forth. By this manner, CryptoNet can perform parallel computation over messages. So after inference, one prediction result, one message we get is for multiple data. However, the limitation of CryptoNets comes from the fact that each feature is represented as a message. This results in high latency because of large number of operations for a single inference and high memory usage because of large number of messages. Besides, it cannot be applied to deep networks such as LXNet. Too many multiplication operations in each layer will increase the noise in encrypted message, thus require larger size of each messages. This makes each operation significantly slow. Shenghui, your turn.
Yeah. Hello, my name is Shenghui, and I'm going to present the rest of this report. And next slide, please. Hello, Mingxian. Yeah, and I'll first talk about the intuition of this paper. And I think this paper is quite straightforward as it has fully used the size of a message. And we all know that for the security concern, the rank of this such ring, that is to say the selection of n cannot be too small, right? And considering we have two vectors, v and w, if we want to conduct the dot product, we will need to conduct 3 addition and 4 multiplications, right? And if there are a total of 8 single numbers engaged. And considering that if you only store one number within one vector, it will be a great waste of space and ability of computation. So what we want is to, rather than, you can will on the second block here, rather than conducting 4 individual multiplication, we would like to fully use the n and store all the fractions or the components of a vector within the different position of a single vector. So the idea is like this: every time we conduct a single product and we will do the rotations. You can view it at the bottom of this page. And next slide, please. Yeah, and I've right on this process, you can say that the rotation should, the n should be selected as a power of 2, right? An integer power of 2. And also the number of rotation operations should be conducted in the following manner of 1, 2, 4, 8, like this. So after rotate 2 times, you will get the result of R2, and similarly, you will finally get the result of R4. And after all the rotation and addition operations, we can find that all the components of the output vector will be the desired result. So you can simply decrypt it and get any of the components, and that is your desired result. So that is basically the idea of this paper and its main contribution, I have to say. Next slide, please. And yes, here is the formalized and generalized algorithm, right? You selected a vector R with size n, and n should be a power of 2, and you will need to conduct like log n rotation and addition operations to get all the components of the output vector equals to the required dot product result, and which accelerates the computation. Next page. And they also categorize different cases when the dimension of the single vector is smaller than the message size n. So I think this idea should be quite familiar with you, right? I think that's about high throughput and has something to do with the scheduling algorithm. And for the also categorize the layers applied in this paper into dense, sparse, and stack, right? They are simply different ways of representing a number or sequence with a vector. So for the stacked and the convolutional case, we can find that a vector can be a number multiplied and or the weights stacked together to cater to a couple of copies of a single number or a single input pixel of a channel. Next page, please. And here's the matrix vector multiplication parts. And we can know that we have dense and sparse. The differences is that if you have like k integers to encode or k fixed point number to encode, this sparse will encode them into k individual vectors, and dense will encode them into one single vector and put that into the homomorphic encryption algorithm. So you have to take different actions when dealing with such matrix multiplication. That is to say, you will like multiply such different vectors with a matrix. So you have to consider use column first or row first. And I think that's about the content of linear algebra, and the author do discuss it in detail. So the principal idea is to analyze the size of the message in a maximal manner. And next slide, please. And yeah, here's an evaluation methodology. And the authors use two straightforward metrics of accuracy and latency at inference time. And the author reported like 100 times improvement, but I have to claim that I think this paper relies on an open source implementation of homomorphic encryption and did not get into the implementation detail. So like 10 times of improvements actually come from a better implementation of this library. So I mean, the performance improvement comes from of the data layout introduced in this paper is also about 10 times. So the authors reported the latency improved from like 200 seconds to 24 seconds, and it has nothing to do with this paper, and this should be noted. And next page, please. And yes, here's the factors influencing latency and shows how the HE, right, homomorphic encryption algorithm works on different networks and how it works in a parallelized manner with more number of cores, and here's latency ratio and the latency. And the blue cross are the self-reported results of this paper. And then we will going to talk about our insights and discussions. And our thing is that I think this paper is more like an engineering improvement and optimization or better implementation, right? It combines some of the overlay, underlay techniques of hardware or data arrangement, data layout. And we can always seek more efficient use of computing and storage resources for higher throughput and lower memory usage, right? Combining with these techniques, and compact data structures and data representation can be a promising research topic, and it can be cross-domain. And also, we concluded some of the strengths and weaknesses of this paper, and I think it's well written, clarified. The idea is straightforward and simple, and the reported performance is good, I have to say. However, we will also point out a few weaknesses, like the result did not claim itself to be a state-of-the-art result, and it used mass passage describing other people's work rather than its own contributions. And we think that maybe the contribution is not very much, since the authors seem to view HE framework as a black box, right? So it only deals with input data layout to get better throughput and performance. And I think it has a lot to do. It's very similar to the hardware fields ways of doing that. So that is basically our presentation, and thank you very much.
Thank you so much. Questions from the audience, other students? Yeah, I think it was one of those papers. I mean, in the realm of homomorphic encryption, one of the key things is performance, and people start using different techniques, as you mentioned, in order to improve it. Of course, at the algorithm level, still there are lots of works, but engineering method like this is also helpful. So I think at the end of the day, it was a useful work. I mean, although it might not be like, groundbreaking, results or something like that, but it helps us to move more toward what we hope to achieve in homomorphic encryption, which is a better performance. But yeah, but thanks.
Yeah, thank you, Professor.
All right. So third presenter, Kiarash. I think it's yours.
Yeah, it's me. Let
You're presenting alone, right?
Yeah, I'm presenting. So I pre-record the video.
Sure.
I think I didn't share the sound. Let me share it again. Okay. Hello everyone. Could you hear it?
Yes.
Okay, before starting it, I want to say I try to make the presentation a little bit interesting, and this overlearning concept is not very hard to understand and very complicated. So I really appreciate if you pay attention and enjoy it. Thank you. Hello everyone, I'm Kiarash, and today I want to talk about the overlearning in machine learning and neural networks, which reveals sensitive attributes and features. So let's begin with an introduction. What does overlearning mean? Assume a model trained for a seemingly simple task. So the objective of this model is only to learn a simple, not important, not private task. But suddenly it learns to recognize specific features and attributes which are not part of the learning task. And these newly learned tasks and attributes are sensitive from a privacy or bias perspective. So suddenly this networks learns some private and sensitive features from the inputs data. And these newly learned features shouldn't, it's not necessary for them to be correlated with the initial task which is supposed to learn. So for example, assume a binary gender classifier. So this model is only trying to classify an input image by gender. Is it man or woman? But suddenly it learns to recognize races. Suddenly it tries to get which race are the people in the photo. And these races were not on the training data. So these training data only labeled as man or woman. But suddenly this network learns the races of the input images. And even these networks and this model, even it may learn identities of individuals. For example, one specific person, it can identify that person from the entire image, which is shocking. There are two consequences with the overlearning. The first one is model's inference time representation of an input reveals the input's sensitive attributes. So on the representation of input data, there are some sensitive attributes. And the other one, which is the more important one, is there is a transfer learning based technique to repurpose a model trained for a benign task into a model for a different privacy violating task. It means there are some techniques that you can repurpose a very benign model for classifying a very non-important task, and you can repurpose it and transform it to another model which can identify a very privacy violating labels and attributes.
Kiarash,
So
can you
this
pause?
is very
pause the video
important
1 second?
in the
Okay, so there's a question. So how do we know or verify that the simple model has learned other features not related to the learning task?
let me read it again. How do we know? So we will get there. I will explain it later. So for example, on the I will elaborate it a lot on the remaining of the presentation, but the key is on the first layer of the feature extractor layers of the model. It tries to identify lots of attributes for in input data, and we can use that attributes to learn and train another model to learn other kind of attributes, and use it to kind of design another model that predict different tasks. For example, we can use the initial model, which is designed just to kind of classify the genders. But on the first layers of its feature extractor, it identifies different attributes, and with exploiting that attributes, we can design another machine learning model to kind of identify races. I will explain it a lot in the remaining of the video. And what's the other question? Not very sure.
But just to help to also add on to what you said, essentially you can define some private task as well, right? So what you can do is saying that, okay, I'm training a model that do, for example, gender classification, all right? And then you train your model. And then what happens is that those private features that you're worried about could be things such as age recognition or face recognition and things like that. So what happens is that what they have shown in this paper was you train a model to do gender classification, but if you also use the very same model for face recognition or age recognition, you will see that your model will also produce really good results. And that means that your model has overlearned those features that are not necessarily related to your primary task, which is the gender classification. Well, let's continue, and then I think probably will be more clear.
Yeah, because this is just introduction. I just kind of cover everything very general. Then I will dive in and explain why. All of this.
Go ahead. Yeah.
Okay. Security preserving area. So another important feature of overlearning is it's inevitable. You know, you cannot make it not happen. Overlearning is intrinsic for some tasks. So it's not possible to prevent a model from learning sensitive attributes. So what does it mean? It means even if you censor these attributes, these sensitive attributes, either their model failed to learn their specific tasks, for example, the gender classifier task. If you censor the attributes regarding the race, if you do it a lot, more than it's supposed to be, the model cannot even classify a gender. And if you don't do it enough, it still leaks sensitive information. So this overlearning is inevitable. So you cannot stop it. So all of the overlearned models have this feature, even you censor it. So why with censoring we cannot stop it? Because there are some decensoring techniques. The authors develop a new decensoring technique. With this technique, and they able to extract information from censored representation. So that's why it's inevitable, because if you censor it, there are some decensoring techniques which can make us able to extract information from the censored data. So this overlearned representation enables to recognition of the sensitive attributes even if they are not present in the training data, and these attributes cannot be censored using any known technique. And this will show the adequacy of censoring as a privacy protection technology. So censoring will not work at all. So let's begin about talking more about the backgrounds. So let's talk about models. So in this paper, they mainly talk about the supervised deep learning. So first of all, these models this learning are supervised, all of them. So we have data and tags for training the model. So let's call our model M, and we have the inputs, let's call it X, and the target with prediction, let's call it Y. So this model consists of two main parts: classifier, which we call it C, and feature extractor or encoder, which we call it E. So as you can see here, this model first convert the input X to the features Z. We call it Z. So the notation is E of X, which equals to Z. So we first convert the input, raw input, to features. Then with the classifier, we classify these features to Y labels, Y outputs. So this is what the classifier does. So this classifier kind of predict the probability of the features for each label. So the label with higher probability going to win the prediction. So usually these features has different layer, multiple layer. So the features from the ELF layer, we call it EL of X or ZL. So there is a technique called model partitioning, which is usually used for privacy, enhancing the privacy. So we partition the model into the two parts: local parts, which run on the device, and remote parts, which run on the cloud. So they kind of put the feature extractor encoder part on the device, which turns X to Z, and they send the features Z to the cloud, which just classify to Y. So there is some for preventing some adversary, they kind of implement the censoring. So this censoring will be here. So with some censoring technique, they try to eliminate the sensitive data in the features from the inputs. So this is the model partitioning. Let's talk more about this censoring. So the goal of censoring is to encode input X into a representation Z such that it does not reveal unwanted properties of X. So the sensitive attributes of the X should not find in the Z. And the Z must have enough useful attributes to predict the task label Y. So the task label Y is the task that we want to predict in our model. And there are two censoring approach. The first one is we train a new model, we call it D. These D try to get sensitive data from Z. We call it S. This S means sensitive data, sensitive labels from the representation of the input, which we call it Z. So this D tries to maximize this equation. It means try to maximize inferring S from Z. But this E and C, which were our encoder and classifier, try to minimize this. It means this model with censoring technique tries to minimize the inference of S sensitive labels from Z. At the same time, it tries to maximize this part, which is inferring the true task, true labels Y from the Z, because it's minus. If we want to minimize this must be minimized and this part must be maximized. So what does it mean? It means this censoring techniques try to maximize the prediction of Y, and in the same time it tries to minimize the prediction of the sensitive data from the Z. And the other approach is this I means mutual information. It tries to maximize the mutual information of Z and Y and minimize, because it's negative, minimize the mutual information of Zx and Zs. It means it tries to maximize the mutual data between Z and Y and minimize the mutual information between Z and the sensitive data. And even Z and X, it means we don't want unnecessary data on the features, on our features. So we only want the useful data regarding to Y. We want to minimize other sensitive or non-sensitive kind of mutual information between them. So there are two ways for exploiting overlearning. So the first one is the inference time attack. So the adversary has a data set. The data set named is the auxiliary data set, the auxiliary. So on its data set, the adversary has a pair of X and S. X is a data input and S is the sensitive labels, attributes that he wants to extract. So he feed its input from the auxiliary data set to our network, M network, and the adversary tried to train another model, which calls M attack. After he feeds X to the our model, overlearned model, it extract its representation and train its model M attack with the extracted Z and its own label in data sets S. After he trained the model M attack, it can use it for predicting given input and its features, which we call it Z star, to predict its sensitive label. But the problem is, if the model implemented censoring techniques, this representation of X, this Z, doesn't have too much information regarding to S. So this network could not work. So you know the problem. They implement the input M, the model M, implemented a censoring technique which eliminates the useful data for training for S. So the adversary cannot train another model on the Z and S because the Z doesn't have enough information regarding S. So now they have to implement a decensoring technique for addressing this problem. For implementing a decensoring technique, they have to convert censored Z into a different form that leaks more information about the property of interest. So remember, the problem was this E of X, Z, doesn't have too much information. So they have to transform it, change it to T of Z. That T of Z kind of leaks more information regarding this S. So in order to do that, they train another network. They call it M auxiliary on the dataset, their dataset. So they train this network with X and S, input and label, without any Z, just input and label. So this network has its own encoder, feature extractor, and classifier. We call its encoder Z auxiliary. So we use its feature extractor. So they kind of use optimization problem. They kind of try to minimize this transformer of Z and try to minimize its error comparing to this encoder of our auxiliary model. What does it mean? It means they try to train this Z, this T of Z, in order to mimic this Z auxiliary. So with doing that, after they done training this T of Z, this T of Z leaks more information regarding to this S. So this time, instead of training M attack on E of X on the pure Z and S, they try to train it on T of Z and S, because this T of Z leaks more information regarding to S, because they train it with the Z auxiliary. And with doing that, they can predict sensitive attributes with given Z. So the second way of exploiting overlearning is the model repurposing attack. So they use M to create another model that, when applied to an input, which called X, directly predict its sensitive attributes. So they try to repurpose this model to another model that directly, with given X, try to predict sensitive label. In order to perform this attack, so we can use the features on different layer of the M model. So we call it ZL. So different layer of the feature extractor layer of the M, we can use it to train another model. This new model calls M transfer with completely new classifier, but as its encoder, it's used M encoder on different layer, and we train this new model on the dataset transfer, D transfer. So this D transfer is a small dataset which itself is not sufficient to train an accurate model for the new task. What does it mean? It means, so why we, instead of doing that, we train our transfer model directly from dataset, because we have X and S, we have data and labels, so we don't need that. So this dataset is small, and if we only train this model with this dataset, it's not sufficient. So we have to use the feature extractor of the overlearned model M. So with doing that, utilizing these features learned by M on this dataset, this model can achieve better result than the model trained from scratch on this dataset. So they showed if we use the overlearned model, if we use its feature extractor layer, we can achieve a better result. So I know it's a little bit boring, but it's almost done. So for the question of when and where and why this overlearning happens, so they purpose this figure. So they learn two different models on different tasks, task A and task B. Task A is the original task, and task B is the predicting a sensitive attribute. So this task B, this y-axis, is the adversary task, and this A is the original task. So they kind of try to demonstrate the similarity between different layer of the feature extractor. So they kind of display 5 different layers from these networks, and these are the feature extractor layer. So as you can see here, on the first kind of 2 or 3 layer of the feature extractor between the benign task and the adversary task, we have a very great amount of similarity. So it means if you, no matter that you train your network for a benign task or adversary task, the first rounds always kind of have a great similarity. So it means that target task is not that important. The networks regarding the task try to extract these features. So and these similarity become higher and higher with more data. So that's overlearning kind of means, because with more data, more similarity between different tasks. So this overlearning will cause serious challenges for regulations. So this regulatories controls the purpose of and the use of this machine learning technology. But the problem is because this overlearning is intrinsic, given a trained model, it's not possible to determine what the model has learned. So the regulators must be aware that even if the original trained data has been erased, this model can be repurposed for a different objective. So it's not possible to envision at the time of original data condition this scenario. So you cannot envision it at the time of the origin. So for example, the user agrees that their data used for a specific task, but you cannot envision what this model will learn. So maybe this their user's data kind of used for different sensitive tasks, and this models learns some sensitive features of the user's data that the users didn't agree with it, didn't kind of okay with it. So this overlearning will cause serious problem, because you cannot know what this model will learn after you train it. So that's the end of the presentation. Thank you for giving your time and kind of listen to my presentation. So if you have any question, I can answer it right now.
All right, great memes. Thanks for the presentation too. Any questions? So people asked questions earlier. Are you satisfied? Do you have follow-up questions?
Okay, ask.
You have a point to make? Kiyosh, you have something to say?
No, I'm waiting for answering the question
okay.
if there are.
No, I think it's doesn't seem to be. All right, so thank you so much. And as I said before, it seems that, we are over the hour, so probably we put the next present. So are the final presenters here, Arjun and Ling?
Yeah.
Okay, so sorry guys. I mean, do you mind to move to Monday if it's okay?
Yeah, no problem for me.
All right. Cool, thank you. So I think it's something that everybody should help. So let's try to make it around 15 minutes so we can actually have all the 4 presentations within an hour. And the reason I'm pushing for 15 minutes is that I think longer it would be slightly, boring for some people because they already read the paper as well. So what I want from you guys when you're doing the presentation is kind of like, use the things that are already discussed in the course, in the lectures, and then what you're saying is basically what is beyond those things that we discussed in the lectures, all right? And then also just share key points of the paper, key results, and so on. Always people can go and read the papers. I mean, all the presentation today was great, but just this point that, moving forward, let's make it compact in 15 minutes so that we don't have these issues like this, all right? So let me take over and talk about the new lecture. All right. I'll give you a second. You can have it like a 2 minutes break. Yeah, Arjun, you had something to say?
Yeah, Professor, is there a sign-up sheet for your project office hour tomorrow?
I didn't. Tomorrow, it's on Friday.
Oh yeah, sorry,
but
Friday.
yeah. I can share something, but you can I'll open the Zoom link from 10. So you can just pop in whenever you want, basically.
Okay, that sounds good, thank you.
Yeah. Okay. Let's have a short like one. Okay, so let's talk about trusted execution environment. So this week we kind of shift our focus from introduction to crypto to more back to more like applicable stuff that we use in this course. So last week we mainly talked about cryptography. We talked about symmetric and asymmetric encryption mainly. Very quickly, I went through the MAC and hash functions. We didn't have time to talk about digital signatures, but as we move forward, we're gonna actually come back to these 3 points again, and then maybe talk about them a little bit more. So don't worry about it if you didn't catch it properly, but hopefully you now have a decent idea of like how symmetric and asymmetric crypto system works, what are the reason and rationale behind it, and so on and so forth. If there are questions about previous lectures, please do post them on Campus Wire, and then we can discuss. All right. So today we want to talk about this very fundamental question is like, how do we trust computer? Like where this trust is actually coming from? And this is like really important question, because then everything else in security standpoint is coming from this very specific and fundamental step and point, right? And the basic idea of the way that we are kind of like build a trust in a computer is there are 3 steps that we kind of need to take. The very first step is that the trust usually should come from somewhere in the computer, right? So the trust should start from somewhere, and that would be the fundamental steps that we're going to talk about, that what is that somewhere and how to do it properly and so on. And then once we actually build that trust and have that what's called root of trust, also once we have that root, the next step is bootstrap that root, chain that root up to the level that we want to. So for example, if you want to run an application, what we want to do is being able to kind of trust the operating system. But how do we trust the operating system? That's the question that we're gonna answer here. That there will be multiple chains here that goes steps by steps all the way to somewhere in the hardware. And this is like the root of trust for us. And we're going to build a system that we are saying that, okay, if we trust this, then there's a mechanism for trusting this. Then there's a mechanism for trusting this. Then there's a mechanism for trusting this. And now we can like, safely, load our application and so on and do it. And that's what's usually called the bootstrapping process or chain trusting process. All right. And the third important thing is not only we have to like, of course, start the trust, then build up the trust, chain the trust, but we also need to find a way to maintain the trust, right? So it might be that at some points, the systems breaks down. We need to rebuild the whole trust, or generally there should be some way of saying that, okay, once I do this, I can trust this for some reasonable amount of time. All right. So these are the main three things that we kind of like in hardware security we need to build. All right. Any questions here? All right. So to kind of like start this process, the very first thing is that we need to, as I said, we need to trust and start the trust from somewhere. And that somewhere usually lies within the hardware. So we typically gonna have what's called a TPM, or trusted hardware module, or trusted platform module. And that's like the actual physical chip that sits inside our computers, inside our motherboard usually. And this is basically where all the trust is coming. And why we are trusting this? Because we are essentially trusting the manufacturer of this. So we are kind of like saying that the manufacturer, for example, Intel, when they're building the chips, they are providing this this security and this trust that this specific chip can be trusted, doing what it's supposed to do. So now, of course, the question might be, how do we trust that? Is that a secure assumption? And that goes into then like further steps down the line, and that's usually what's called supply chain security. Or like, implementation of hardware security. All right. We actually gonna like spend about a week or so on this topic as well, not specifically about the supply chain, but hardware security in general. But for now, just assume that the process of, designing and manufacturing and building a piece of hardware inside a company such as Intel is trusted and can be trusted. So let me see. Somebody asked a question. So by trust, do we mean how do we trust our computers to not send our private information to malicious people? Yeah. So by notion of trust, it means that expecting your program or your entire device to do what it's supposed to do, or to do what you expect it to do. So for example, if you're sending your information to a cloud, that doesn't mean that you are breaching the trust. You are voluntarily sending your information to the cloud. But if you're doing the processing on your device, and for some reason your device is recording your information and then sending it to some outside world, then that's the part that it shouldn't do, right? So that's the part that you're not assuming, right? So for example, if you are using a cell phone and then you're disconnecting the network and everything, it assumes that everything stays on that local machine, right? If it doesn't, then it means that the trust is, I mean, again, the notion of trust here depends on the threat model as well, like what we're doing, what we want to achieve, and so on. All right, so back to the point. So we said that essentially assuming that this supply chain can be trusted and this process can be trusted, we are at that point that we have kind of like we have the core or the seed of the trust on this module, this Harvard module called Trusted Platform Module, or TPM. All right. So then what? So then what happens is then we need to kind of find a method for bootstrapping this this trust. And this bootstrapping usually happen in the booting sequence. So essentially, whenever you turn on your computer or your mobile device or whatever computing device that you have, what happens is that it boots from this TPM, and this TPM is actually the ones that takes over at the very, very beginning, and then everything else is basically builds off of that. All right, so that's the boot sequence. And we want to talk briefly about like how this boot sequence happens and what is exactly done in order to make sure that the security of the system is maintained and is actually achieved. Any questions so far? All right. So here I'm gonna just give you one example of how this boot process is happening. Actually, it's not necessarily just only one example, one way of doing it. There are multiple different ways of doing it. But what I'm showing here is kind of like one type of system level behavior that you would see in modern computers. This would be basically the basic block of your motherboard. You have multiple different units such as the CPU and the RAMs, and these CPUs are connected with multiple different network on chips techniques. It could be directly point-to-point connected. It could be some sort of mesh connected, so on and so forth. We don't pay attention to that. Then usually there is some sort of like a network, physical layers of your network, and there is some sort of like a flash memory here. That's most of your boot sequence that we're going to talk about sits here. And then there's this, this security parts that, oversee all of these. We're going to actually talk about PCH and what it stands for and so on. All right. So now let's go and talk more about this part. This is actually where, in this specific example that I'm giving you, this is where the whole notion of boot sequence and bootstrapping happens. All right. So again, the naming could be different from, for example, AMD models, from Intel models. This is borrowed from an Intel chip, but even in Intel, they typically change their names. So don't get confused if you see a different names sometimes for these chips. To just get the overall idea of what we're doing here. All right. So generally, what is boot sequence? Boot sequence is essentially a series of programs, or you can call it firmwares, to initialize different part of the motherboards. It doesn't necessarily have to do with the security. So whenever you want to start using a computer, you need to load all the drivers for your IOs. You need to find all the memory addresses, load the virtual memory addresses, and eventually load your operating system with all these tables and all these connections. And then the operating system takes over after that. So that's mainly for systems with the operating system, which we're going to mainly talk about in this lecture. The idea is that somehow, load that operating system. And once the operating system is loaded, then essentially the operating system becomes the software that takes over everything. And everything else is kind of like interacting, interfacing with the operating system, right? So that's what we want to do with the boot sequence. But one of the essential part of the boot sequence is establishing the security and trust. All right. So let's see how does that happen. So as I said, the very first steps of building this trust relies on trusted platform modules. It's a piece of hardware that inside the piece of hardware is actually a key pair and some of the cryptographic functionality that he mentioned. So remember I said, for example, in order to do symmetric encryption or asymmetric encryption, we need some secret key, right? So that's actually where that secret key is going to go inside the hardware. So essentially, think about Intel as this intermediary that has lists of numbers, which is basically our keys. They use some sort of key generation techniques that is secure. And whenever they are building a new chip, they're going to just pick one of these and put it here into that. And they're going to keep a record of these, obviously. And they also, if, for example, we're going to use an asymmetric encryption mechanism, they will also publish the public key of this core and this piece of hardware to the outside world, and also put that pair with the secret key inside the hardware as well, so that if the hardware wants to announce it to someone, they can do it as well. Not only that, usually inside the TPM there are some logics as well. And those logics are some cryptographic functionality. Mainly, the main thing that's the mostly used is a hash function. It's a secure hash function. That what it does is basically, given some inputs, it will compute the hash of that inputs and send you the hash, all right? And use the secret key in order to create that hash, right? So that's the main functionality that it's need. And then there will be some other information necessary for for doing the bootstrapping that we're gonna discuss. So basically, it's just some secrets, some hash, and some critical values that we're gonna use later on in the system. So that's essentially what the TPM is, right? So somebody asked, I'm still trying to better understand hardware and software role in implementation and trust. Would it be correct to say that in some application, a main rule of hardware is this bootstrapping and creating layers to the OS that may not be trusted? So for now, we are assuming that the OS is trusted. So we are not going into one step further that what happens if the OS is not trusted. But we are saying that in order to fully load the operating system securely, what are the steps? All right. So because let's say the assumption is always that this computer, this hardware, unless it's not compromised, can be trusted. So what is that initial phase that we kind of always trust that system? Because what happens is that we're going to first load that initial phase. And what happens after that is out of our control. Well, what is in our control is actually at least initializing the system to a known good model, to a trusted model. All right. So that's what we're trying to achieve here right now. Okay, cool. So the TPM is our root of trust. And as I said, we want to eventually load the operating system. And here we are guaranteeing that this operating system is in an initial phase that can be trusted. What happens after? Out of our control. Okay, so how do we establish the chain of trust? This relies on this functionality, this primitive called attestation, right? So what the attestation does? Attestation is just basically this, we call it, let's say, call function F. So what attestation does is that, let's say we have a programming question X. So just think about X as list of values. So what happens is that essentially any sort of firmware or software can be shown as list of instructions, right? So just think about it as list of instructions. And list of instructions at the end of the day is basically nothing but a bunch of zeros and ones, right? So at the end of the day, this is just a string of zeros and ones, right? So what this F does is that it takes this it takes this X, then compute the hash over this, right? The secure hash, and then output this Y, right? Then what it does is that compare this Y to this Y prime. And if these two are similar, we say that the attestation has been succeeded. If they are not similar, then we are saying that this attestation is not correct. And what is this Y prime? This Y prime is actually the pre-recorded hash function for this X, all right? So it's kind of like the ground truth for this X. Why this makes sense? So let's say, for example, we've written a program X, and we are the one who written that program, right? So what we do is that once we write that program, we also compute the hash over this program, and we call that Y prime. So whenever we're gonna send this value, we're gonna send a pair of X and Y prime. So everybody knows that this is the corresponding hash function to that X. So the idea here is that if somebody else tries to change the X and change the X to something else, X prime, then what happens is that this attestation value, this hash value would be different than what it's supposed to be, right? So it would be Y double prime, which is not equal to Y prime. So we can easily and quickly detect that whether this X has been modified or not modified, right? So this attestation is generally referred to this whole functionality, right? So what we are doing is this function gets whatever inputs that you want to attest. It computes the hash over it, and then it also reads the Y prime and computes these two, compare these two. If it passes, it means that X is not modified, so X can be trusted. So somebody asked, can somebody not change Y prime also as well? That is correct, but if I go back here, that's actually, remember I said in the TPM, we have list of some values that is important for us. One of those values is actually this Y prime. So essentially there are lists of software that we're gonna, list of firmware that we're gonna attest and use in TPM. what TPM does record is all of those values in its memory. And since the TPM is trusted, means that nobody can actually intervene and change things inside the TPM. So the TPM is designed such that nobody can actually change things inside. Harry?
So, Professor, in briefly, trusted platform module is the hardware which kind of safeguards this, like this trusted computing base, the key or like the hash that we store here.
Exactly.
Is that it? Okay.
Yeah. Any other questions? Okay. So, Sarthak? Sarthak, are you there? You're mute if you're talking.
Yeah, I'm so sorry. I'm sure there's an answer, but I still want to know what is stopping us from having a TPM for storing the entire flash to just, I mean, it would be secure then. Because we can assume that the TPM is secure and it is supposed to not leak any information to malicious intents. So why can't we just have an entire flash stored in a TPM and work around, I mean, have an easier solution than this?
Well, why your entire flash being like TPM would help you? So first of all, TPM, so two things that you're kind of mixing up. So one is that, you know, your system cannot be attacked in some sense, right? So let's say physical, or this depends on like how do you define it, right? So you can build any hardware to be resistant, for example, against physical attacks. That's a separate story than TPM. One feature that TPM has is that you cannot, you know, probing and this anti-probing, and you cannot do physical attacks on it. But at the end of the day, how does, like, you know, putting flash into TPM helps? I'm not entirely sure what you're saying.
I was just thinking that, I mean, we see that maybe the flash is overwritten by a malicious firmware, and we have to check its verify its identity to trust it.
Yeah. So for all the firmwares that leads to loading the operating system is actually part of the TPM itself, not the entire values, but the actual checkpoint, the attestation value. And the reason that we are not saving the entire firmware inside the memory of the TPM is that it's not necessary, right? All we need to know is this checkpoint value here. If I have this checkpoint value, whatever I store outside, I can always verify that storage, right?
Okay.
So
Yeah.
as long as this functionality is done securely, right? And this value is not modified. So all I need to secure is F and Y prime. If I can secure these two, I don't need to secure X, right? Because even worst case scenario, if somebody change X, it's going to go through the F and it's going to create Y double prime, which is not equal to Y prime. And that answered the question. Right?
Okay, yeah, thanks.
Yeah. Because on the other hand, then you have to store this really big firmware value into this, you know, secure memory, which is not a good idea.
Yeah, okay.
So somebody asked, is X usually a user program or firmware? So for now, we are just talking about the boot sequence. So what we are trying to secure is the boot sequence. So in this case, the only thing that we attest is the firmwares that requires for the boot sequence. So loading drivers and loading the tables for the operating systems, essentially what is required for the boot sequence. All right, Blanker? Okay. Okay, so going back here, we wanted to say how TPM is used to build a chain of trust. And we're going to rely on this concept called attestation. So let's see how. So essentially the idea is this: we trust the base, which is the TPM, and then ask the base to compute the hash of the next phase, and then move to the next phase. And now we're starting from the TPM. We ask the TPM to compute the hash for whatever next function is, next operation is. Let's call it C1. And if the TPM actually attests this and computes this and see that it's actually correct, Then this part is trusted. It has not been changed. And now we can say that, okay, do whatever you have to do. And once you're done, what you need to do is that computes the hash of the next step, whatever that next step is. And then if this hash function and this attestation is successful, then we can trust C2. Then C2 starts, do whatever it has to do. Again, it's going to do the next steps and next steps and next steps. And this process continues until we actually reach the point that we load the operating system. And that's where the operating system will take over. And the rest is, everybody knows how it works, right? So that's the key idea, that we start from here, and the trust from here is actually coming from the manufacturer. TPM has the functionality of computing the hash. So thankfully, it can actually compute this hash here, send it to the next one, and then that's it. All right. So somebody asked, how does the TPM distinguish between the user updating the driver from a malicious software? So that's a great question. So if this, so there is this notion called secure update. That what happens is that when we are updating some driver, we need to also update the hash function inside the TPM. All right. So that's why for these critical parts of the program inside the motherboard, you cannot just go and update things. There's a special process for it, that how to do that and how to update the TPM. Actually comes from this fact that there is this thing called digital signatures that once we will talk about it later, but essentially, for example, the manufacturer of that specific piece, let's say Cisco, if it's like a physical, modem or driver, or that specific driver, they have to authorize and say that this is actually coming from us. The way that they do that is using digital signatures. They sign their update with their own secret knowledge, and everybody can verify that it's actually indeed coming from, for example, Cisco, whatever company that is making this. And that way they can now securely update their TPM. All right? Does it make sense, Ara? Okay, cool. And so, yeah, so that's how we do it. TPM, next phase, keep repeating until we reach the operating system. Now the operating system is loaded, then the job of the TPM is kind of is finished. It can sit back. There will be some other things that TPM might be, queried for, but for now, for the boot sequence, basically that's the end of the story. All right. So this is kind of like, giving you some examples. So the UEFI process is one of the ways of, booting computers. The unified extensible firmware interface is kind of like this, that, this secure part is actually where this stands in the TPM. And then there are a bunch of different steps. If you're interested to see what each step is doing, probably you can just Google UEFI and learn about it. It's not part of this course. It's more of like an operating system, functionality. But the important thing that I want to show you here is that basically this step-by-step approach, that this measure here means that the attestation measure. So basically the security, just look at this piece of code as sequence of zeros and ones, compute the hash. If the hash is what is stored already in the TPM, then mean this is trusted, so we can actually safely jump from this point to this point. Same story from here to here, from here to here, until we reach that point that we load the runtime, which is the kernel module of the operating system, and then we are done. All right. Any question? All right. So, and then in order to actually having this chain, the trick is that whenever we are, computing the hash of next steps, we also add the hash of previous step, all right? So basically the TPM, in order to compute the first hash file, so we usually let's say the bootloader is the one that we want to verify. So we first compute the hash of this. We send it to the TPM to verify. Once it's verified, this value is going to be added to some values that's coming from the TPM. This value is going to be then added to this part. And then again, if we want to, for example, check the correctness of the OS kernel. We first compute the hash of this. The TPM will check this, but then we put it here as well. So we chain this in order to, like, whenever, so we don't, like, we prevent the system from replay attacks. And we always, like, by checking this hash function, not only we are checking the correctness of this, but it also guaranteeing that everything else before this is also have been done correctly. So somebody cannot just, find the hash function of this and then attack the system, because not only this is part of the hash, but also all the things that has been, computed before is also coming to the hash. So this way we kind of like, do the chaining in order to make the system more secure. All right. Any questions here? And here we kind of like showing this, we summarize kind of like the steps before. So here basically we are only checking the bootloader, the OS kernel, and the kernel module. And at this point we have the operating system fully loaded. So basically you can think about this as main 3 steps that we really need to care about. All right. So going back to here, as I said, all these parts is usually done inside this PCH. The PCH is the stands for the Platform Controller Hub, or as I said, PCH is something that is that's created by Intel. So this is a terminology that's used by Intel. The PCH is basically, to give you a little bit more information on how it works, is this always on module that it has its own core and memory. So it's kind of like completely independent from the actual core on your system. So it just sits separately from all the other cores and the memory and everything else that you have in the system. And what it does is that it has a bunch of different, engines and cores. So, and the main part is this Intel ME, which is the management engine of the system, that it runs multiple different things. It runs the accelerator, controls the cache, the boot, the other, like, communication with the outside world, such as the SPI controller and so on and so forth. So all these different, drivers and modules that we kind of like use is actually sits on this Platform Controller Hub. And that's where we need to kind of like, check the correctness of all of these things inside the system, all right? So that's where, and what we really need to trust. So when we are talking about the boot sequence, we are basically, making sure that all these modules are correctly loaded and they are the same values that we are expecting them to be, right? So yeah, and part of the PCH, I'm not sure if we have it here or not. Yeah, we have the boot ROM here. I'm not sure. I think it's so they have the accelerator here, but the TPM essentially sits here as well. All right, so that's where the whole thing happens. Okay, there's no question here. And so, yeah, so the PCH is always on. When you turn your computer on, it basically, what happens, it tells the PCH to invoke the UFE and then tells the TPM to initiate the process. The bootstrapping goes step by step as I described. Then the system software will be fully loaded. And then after that, the execution will be taken over by the operating system. And now we have a fresh operating system, reads from the memory. The idea is that now, okay, we have the initial phase of the operating system, we can trust it. And the rest is basically goes into the territory of how do we secure the operating system? And it's a completely separate story that we need to talk about as well. Any questions so far? So if the attestation does not succeed, the boot sequence will fail. So usually some error will be thrown. So you will see some sort of errors that says that, the system cannot be trusted, the driver has been malfunctioning and so on. Usually there's a way to recover it, and that depends on, so as I said, the PCH usually has its own core and memory. So there's usually an interface between the PCH and the outside world. It really depends on the motherboard and the systems that provides this interface, but typically there is some interface in order to fix this. Because again, if you want to update some of the critical firmwares, we need to also come with, we need to also update that UEFI. Typically, there is an interface between UEFI and the outside work. Yes. Cool. Okay, so obviously the main question is that is this actually a secure way of doing this? It's fairly secure. I mean, the process of booting is something that's been secure. The only problem is vulnerability against physical attacks. When we get to the physical attack part of this class, we're going to talk about what they are, what they can do, and how, for example, a boot sequence can be attacked using that. But essentially, against any internal adversary, any digital adversary, the system is very secure just because the TPM does its jobs properly. Of course, if the TPM cannot be trusted for any reason, then the whole system breaks down, obviously, right? So that's also another key part. So that's it with the bootstrapping process. If there's any more questions, feel free to put it on CampusWire and we can talk more about it. But now let's actually think about, okay, now that we have, fully loaded the operating system, what happens next, right? So this part we now already know how it works, but now we want to run specific software within an OS, right? So how do we guarantee that that software specifically is trusted? And the second thing, that how do we trust the operating system itself? How to trust. So why the OS cannot be trusted? Because OS is essentially a piece of software itself. And given the complexity of the operating system, there are many known attacks to the operating system itself. So although it's been fully loaded securely, as it progresses, as that time goes by, and interfacing with outside world with a network, unfortunately, there are known attacks that attack the operating system and break the assumptions that we have about the operating system. Yeah, somebody asked, since the SHA algorithm is the same to two PCs with the same firmware would have the same hash output. And that is correct. One trick usually is that, when you're initializing it, the TPM, what it does is actually create a nonce, very same way that we did it for encryption. So remember that I put here, if you pay attention to here, so what it does is basically put this, we show it as 0 here, but this number could be any nonce value that the TPM knows. So when it does it, it actually put this value here as well. And then as we move forward, this value will be propagated. And the nice thing is that TPM would be the only one who knows what this nonce is. And TPM, in that case, then would be the only one who can verify this. All right. So this way we can kind of prevent replay attacks, because with the replay attacks, you will see the hash one time, so you can just record it. Next time that you invoke, you can just give that hash function, right? But with this, if we change the nonce every time, then it's guaranteed that every time you will get a different hash value. Okay, so let's see how these two questions can be answered. So for the software itself, unfortunately, the answer is we cannot include every piece of software that we want to execute on our operating system in the boot process. So of course, an easy answer would have been that I put this in the boot process as well. And then when I'm doing the hash, I also compute the hash of this, compute the hash of this, compute the hash of this, compute the hash of this. And this way we can trust all these applications as well. But the number of applications are too many. This is not scalable. And then another thing is that the application themselves can be quickly changed, and changing the checkpoint value in the TPM is not something that we can easily do, right? So it's not possible to actually, for every single software that we want to run on the operating system, we need to reuse that. So what should we do? The answer is two things that we can do. So if the operating system itself can be trusted, what we can do is that using the same trick that we use for TPM, instead of storing the checkpoints within the TPM, we can store the checkpoints within the operating system. So essentially, whatever the application the operating system wants to run, assuming the operating system can be trusted and it's not being attacked, we just first do the attestation of this program. So program A comes in. So the operating system first do the attestation, compute the hash, compare the hash with this value. If it fits, then say, okay, A is trusted, so go ahead and execute, right? So that's the idea that we do. The things get very challenging once the operating system itself cannot be trusted, all right? So if the operating system is no longer known, the state of the operating system is no longer known, then we are reaching to that point that we have piece of software that we want to run on this specific hardware, but the interface with it is this operating system that we don't really trust. It not because the operating system is compromised, it could be for privacy reasons as well. So for example, we have a piece of data, we want to send it to the cloud, but we don't trust the cloud. But on the other hand, we want to really use the cloud. We want to use the hardware, the powerful hardware or GPU that exists in the cloud. So what should we do? The idea here is that we need to use some sort of outside methods for this. And that's rely on the topic that we want to talk more in the next lecture, and that's the trusted execution environment, right? So what is trusted execution environment? So trusted execution environment, as the name suggests, is an environment that includes memory, part of the core, some runtime activities, and so on. The main idea is that we reserve part of the hardware and make sure that the operating system cannot control it. So for example, if we have, 2 megabytes of memory, how about, for example, we reserve small portion of it, let's say 100 kilobytes or something, and say that this part, the OS cannot access this part. How do we do that? Basically, we can do an access policy. So we put a piece of hardware here. So whenever the operating system sends addresses that falls within this range, this access policy, which is part of the hardware, just blocks this access. How do we trust this piece of hardware? Again, this becomes same as any other IO platforms that we have. So we can easily put this part in our TPM as well, all right? So essentially all we need to do is so within our boot sequence, we need to verify the status of this. If we verify it, then we can know that this can actually sit between the memory and the operating system. If the operating system tries to address these addresses here, this module will block, all right? This hardware resource is a non-volatile memory. Which hardware resource? No, it's not. It's volatile memory. We just reserve it. So think about this as addresses. So for example, let's say addresses starts from 0 to 2 megabytes, right? 2 to the power of 21, right? 20 minus 1, not 21 minus 1, right? So what we are saying is that the addresses that fits within this range that goes from 2 to the power of, for example, 12 or below, if the operating system tries to actually access this physical addresses, we're just going to block it, right? So that's the whole point of a trusted execution environment. We're going to actually talk about the exact implementation and so on, but just know that the idea here is that we reserve part of the hardware and make sure that the operating system by any means cannot access that, all right? Then what we need to do, we need to find a way for an outside application, the application that does not sit on this computer and not controlled by the operating system, be able to access this reserved part. So we usually call it remote code execution. So we need to provide this methodology for an outside system to talk to this part of the hardware. So what will be the applications? There are two main applications, right? The main application is security. So essentially, if the operating system is not trusted, but we still want to use this piece of hardware, if we actually use a trusted execution environment, we don't care whether the operating system is trusted or not. It's always guaranteed that the system works correctly, right? So we lose a large part of the system, for example, in terms of memory, we lose all these things here, which is like, 90% or something of the system, but at least we get the trust that we want. And for some application that could be useful. Another more interesting use case is privacy. So remember we talked about privacy preserving computation, and we essentially said that the problem is that piece of data and some function, and we don't trust the system that runs this function, right? And that's where we come up with all this idea of homomorphic encryption. We basically said, okay, let's encrypt this, or we said multi-party computation. We said that, okay, let's collaboratively do this, and so on and so forth. So we go through all of those things. So this trusted hardware execution, it actually can answer that question also pretty interestingly. Why? Because essentially what we are saying is that we are not trusting this hardware, but we are trusting a tiny bit of it, which is the trusted execution environment. So we only send our data within this, and we make sure that this system does not send the information to the operating system itself. So it doesn't send it to the outside world here. And this way, our data is guaranteed that it's going to stay here. And this way we can still use this computing platform here. Of course, we're not using the entirety of it. We're only using this small portion of it. But if this small portion is much more powerful than what we have here as the local computer, which in reality it is, then we kind of like, get the best of both worlds, right? So we can load the information here, we can execute it here and get done with it. And what is the benefit over this T versus, for example, homomorphic encryption and multi-party? The main benefit is that you can just do the computation here normally, right? You don't need to encrypt anything. You don't need to do multi-party computation or anything. You just send your information here, and you just do the execution here without any problem, all right? So you get a much more better performance. So that's it for today. We're going to talk about real world examples and how do we actually implement this in real world. Specifically, we're going to talk about Intel SGX and ARM Trust Zone as the main two industry standards for this. We're also going to talk about some other options that academia come up with, such as Sanctuary and so on and so forth. So we're going to talk about this option as well. To see how do we actually do that reserve part. So there are two things that we need to do. We need that hardware enforcement or that reservation part. And then we also need to find a way for remote execution, right? So we need to come up with an idea that how we do this remotely as well. So that's what we're going to talk about on Monday. And then if you start reading the papers, you will see that it's going to be about these kind of things. All right. Any final questions, anybody? Great. So I think we can end the class a little bit early today and see you guys next week. All right. And then if those of you who wants to talk with me on Friday from 10 to 12, I'll be available on the same Zoom link.